Okay, this video is going to be about the GS2 drive. So we're going to take a quick look and see what this is all about. You can see that this is the front cover to the manual. Excuse me, for the manual, user manual for the GS2 drive, and it shows that I've got a number of possibilities here for inputs. You can see it's 115 volts, 230 volts, 460 volts, or 575 volts. And they also list, along with those voltage ratings, the horsepower that you can run with that particular type of drive. Okay, here's our trainer. You can see that its arrow does not show up here, so I can't really point it out. But anyway, the first red arrow that you see going over there from the first paragraph is talking about my power supply that I've got running this drive, and this is actually a single phase 120 volt AC input to this drive. That is a 20 amp breaker. It should probably be a lot less than that, but this was what I could put together in a hurry so that I could have something to demonstrate for you. Okay, the breaker is also used to turn power on and off to this drive. If you look at the second red arrow down, it is actually pointing at the interface panel. This is where, when you get this drive, if you've ordered what would be referred to as an HMI, a human machine interface, this panel is where you can program, you can start, stop, turn the speed up, turn the speed down, and so on. These are all where you can do all your programming for this drive and operation of this drive if you wanted to. Oop, one too many. Okay, that panel, okay, if you look where the arrow is pointing, can actually be removed. Okay, so it's got a little clip on this side, there's one directly across from it, and there's a little indentation in the molding there. So you can reach in, grab those clips, and you can actually remove or pull out this interface panel. So if you wanted, or you were on a budget, you had several of these drives, you could get just one of these panels and remove it after you've programmed the drive and go to the next one and download the parameters to the next drive. So you could use only, or need only one of these to do your programming. In industry, we had one on every one of the drives we used. It just made it easier for troubleshooting and for programming. Okay. What else is shown here? You can see that on the sides there are little louvers or cuts or openings in the side of the drive that is on the other side and on the top as well. Those are for heat dissipation. They are used to remove some of the heat. The drive does actually build up a little heat when it's running. So this is a way to dissipate some of that heat. Behind the drive, on this trainer, you can see the back half of an AC motor. Okay, so that is where the cooling fan of the AC motor is located. In this picture, you can get obviously a better view of where my supply power comes in, where my voltage going out to the motor actually goes to too. So you can see that the red wire is my hot lead going through the breaker, and that goes to the drive to supply power to it. And then if you look, they've actually color-coded my wires coming from my source. I've got white, red, and green and yellow. Of course, the white is my neutral, the red is my hot, and green and yellow is my ground. So those are all wired in here. So this is where my supply comes into it. The black leads are what are going out to the motor to run the motor from this drive. There we go. Well, when you're going to set up a drive or you're going to set up a motor to be run off a drive, you need to choose or pick the drive that you need based on the motor nameplate information. So you can see that on the side of the drive there is information as to what model this is, and this particular one is a GS2-10P5, and the motor nameplate is right there, and that is more of a European nameplate, and we'll go over that a little bit as well, so you got some idea of how to read that. Okay, there's a close-up picture on the left there of the nameplate going to, or that is attached to this drive. And here's some information about that. So mine is the GS2, and that's the series name. The 10, in this case the 1, I should say, it's 10. So you start with the 1, and you can see that input voltage for 1 is 100 to 120 volts AC. And then it would be 0P5, and if you look at 0P5 where I've got the red arrow, you can see that it can handle up to half horse as far as the motor size is concerned. There is also this chart below that, and you can see in the chart that I've circled the 10P5, and you can see it talks about a half horse motor, 0.4 kilowatts of power, and then your output current, which is 2.5. So you need to know how big is your motor, how much current do you draw when you run the motor at full speed, at full load amps. And of course your kilowatts, you can determine between the current and kilowatts what your voltage level would need to be as well. So with this particular drive, you know what your input is, you know what your output is based on the motor. So we'll take a closer look at that as well. Okay, this is inside the motor housing where our wiring goes in. This is the cover. It shows that I can either connect it in a Y configuration or a delta. When I took the cover off this motor, you can see it is connected in a Y configuration. If you look at the cover, you can see that W2, U2, and V2 are all connected together. And if you look to the picture on the right, you can see a metal band that runs from each one of those from left to right on the top half. On the bottom 3 screws, I've got my T1, T2, and T3, or those are the leads coming from the drive going to the motor to run the motor. Here is the motor nameplate on the left, and you've got the cover on the right, and then down below the cover I've got delta and Y, or excuse me, star and delta, and star is also considered Y. So they can call it either Y configuration or star configuration for your wiring. That's how the motor was originally set up, in a star or a Y configuration. So I'm going to look at my nameplate now on the left. First thing we need to do is figure out, well, is this the right horsepower? How did I come up with 1/20th of a horsepower? Well, 746 watts per horsepower times 1/20th equals 0.37 kilowatts of power is needed. Okay, so I looked at that, and if you look at the nameplate, you'll see just below where it says DIN, you'll see a 0,37 kW. Well, what they're talking about there is 0. I don't know what, they must not have had a decimal point, but that'd be 0.37 kilowatts, and that does figure out to 1/20th of a horsepower. S1 is a service factor of 1. The rest of that is, you don't have to worry about it. IP55, all these things have some meaning. You could definitely look them up, but for this short video, I don't want to take up a lot of time with that. Okay, so now if I do the Y configuration or the star configuration, drop down where you see that 37 kilowatts, and you'll see that the next line is 1370, 1660, 1700, Those are all RPM ratings. Well, right now I'm looking for voltage ratings. So I drop below that, and you see that it shows the symbol for delta and Y. And the first group there is 230 and 400. So if it's wired in delta, it's 230 volts. If it's wired in Y, I can run 400 volts to it. The next group is 230 to 400, and then the third group is 275 to 480. Okay. So those are the voltages that I can run on delta and Y configurations. Now our drive is only capable of 240 volts. This motor was wired for 480 volts in a Y configuration. So since the drive can only put out 240, I need to change to the delta configuration. So I need to have that lower voltage. So how do I determine which one of those lower voltages to use or which one of those to use? You see again, the 230-400, the 230-400, and 275. Well, the last one, the 275, you know we can't use that because I'm only capable of putting out 240. So it eliminates that last one. But now I've got to look at the 230, 400, the 230-400, both the same. So how do I decide which one of those to use? Well, if you go back up to where it says IP55, which is the second line down, you'll see that they've got 50, 60, and 60, and those are all frequencies. So that's hertz. Well, we run here in the States 60 hertz. So I know that that middle one, where it says 230-400, is the one I want. So I need to set it up for 230 volts, and it has to be a delta configuration. If I drop below that line there, you'll see that I've got 1.84, 1.06. That's for the first group. We're working with the second group. So at 230 volts, I have 1.65 amps that it's going to draw for that particular motor. And that's what I've got listed down below. So I'm going to have to change it to a delta configuration. I'm going to have to program my drive to put out 230 volts AC, and I have to have a current capability for this drive of 1.65. Okay, so I have to move to this configuration. I've got it circled there. You can see that it's W2, U2, V2 are all tied across to U1, V1, and W1. And if you look closely in the picture over there where I've got my other red circle, you'll see that I've put the bars, instead of straight across, I've connected them from one side to the other. And the very top one you can see says U1. So I've got U1 going to U2. That black wire is kind of blocking it, so you can't really read it. V1 to V2 is that jumper. And last one would be W1 to W2. So I've now configured the motor to be wired for a delta configuration. So again, the motor is capable of being run at 230 volts. And again, we're doing this because the drive is only capable, this particular drive is only capable of putting out 240 volts AC max. So that's why I had to change the wiring on the motor. Okay, these warnings, I'm not going to spend any time on them. Make sure you do take the time and look them over. If we were actually going to put this into service on a machine someplace, we would have to go through each and every one of those. Because I want to make this video as short as I can, I'm not going to spend any time on them. Okay, this I thought might make a little more sense to you, so I'd put this in there in case you come across any questions on it. Because I'm calling it a frequency drive, just remember there are other names for the same thing. An AFD, which is adjustable frequency drive, a VFD, which is variable frequency drives, inverter drives, and so on. So there's a lot of names for the same type of drive. Their primary purpose is to be able to vary the speed of a three-phase induction motor. And they also provide non-emergency start and stop control, acceleration, deceleration, overload protection. And because you have that capability of controlling the speed, that also controls your current draw. And that will reduce your inrush current to this motor. The reason that is so important is because the power companies or your utility company bills you according to your peak current draw or voltage level. So when I first turn on a motor, if it is an across the line motor starter, meaning that I've just run full tilt of voltage to it, that would be at inrush current, and I'm going to get a spike at inrush current. Remember, when that spike comes in, that's what the utility bills you at. So that spike could be 6 to 10 times higher than what I'm normally going to run at, but they're going to bill you at that 6 to 10 times higher than I'm normally running at. That is how they set their billing for these things. So by using a frequency drive and ramping the speed up, I can actually keep that inrush current pretty low, and that will allow the electrical bill to also be lower than what it would be for an across the line starter. Okay, there are actually three main parts to a frequency drive. We got a they say converter rectifier. I always call it the rectifier. You got the intermediate circuit, and you have the inverter. Okay. The single phase rectifier, if you look at this, and again, I don't seem to have my pointer available to me, but the positive side is going through the diode on the top. So it would go up and out the top of this. So that would be your positive, what they call bus voltage on that side. And if you look at the negative one going to the second set of diodes, it would be going through the bottom diode. So the bottom half of this drawing would have your negative half on it. Because this is uses frequency coming in with AC, that means the second half of that sine wave is negative. So if I reverse those plus and minuses that you see there on my voltage source, and now I had the minus on the top, it would no longer go out through the top, it would go down through the bottom. And because now the bottom half of the voltage source would be positive, instead of going out through the bottom, it would go out through the top. So what I would have is a pulsed DC coming out of this. Okay, the intermediate circuit takes that pulsed DC, and I don't know if you notice the capacitors, inductors, and so on, but what it does is it smooths it out and gives you a more stable DC voltage and current. The inverter takes that DC voltage, and again, the top half of this would be the positive, and the bottom half would be the negative, and it switches the frequency, or it switches those transistors on and off in a way to give it a what do you want to call it? A DC, a simulated AC sine wave, and that's what you're seeing over here. If you look at the first one where it says switching frequency low, you can see that it's pretty jagged. It isn't a real smooth sine wave. And then you got a medium, it looks a lot smoother in the middle one, and then of course if I'm at a higher frequency, because it's switching so rapidly, you can see that it looks really clean and smooth. And that's how it will take DC and make it look like AC. Okay, here is the complete circuit. Again, on the left-hand side is your rectifier. Your intermediate circuit is in the center, and then over on the far right where you've got your transistors is your converter. Notice that my three leads from the motor are tied to the three legs of my DC source. So if S1 is conducting, I'm sending the positive to that first lead going to the motor. By the first lead, I'm talking about the top lead. If S3 is conducting, I'm sending positive to the second lead. And in this case, I have to have a negative for my third lead, so S2 would have to be conducting at this point. So S1 and S3 would be positive, S2 would be negative. At any one time, I have to have at least two of these transistors conducting electricity. Just one conducting, nothing happens. And I have to have a positive and a negative to get current to flow through this. So again, I have to minimum have two, and I could possibly have three of these transistors conducting. So S1, S3, and S5 are all my positives. S4, S6, and S2 are all my negatives. Okay, there is a closer look at the faceplate and the motor. They're talking or showing a bunch of different parts to the motor. You can see that there's a cover on top and a cover on bottom that are hinged so that you can connect your wires up to it. And of course there are mounting holes or openings. This can also be DIN rail mounted as well. So there's a lot of things going on there. There's actually some switches that can be set as far as number 7 is pointing that out. Number 8 is where my power comes in. Number 10 is where my power goes out to my motor. You'll see that there's a T1, T2, T3, and there's also a B1 and B2. The B1 and the B2 are for braking resistors. Number 9 down there in the lower picture, those are all my connections for having remote operation for this drive. In other words, I want to have the operator capable of pushing a button on his panel to start it and so on. So that's where I make my connections to set it up for an operator to run it from a remote location. Okay, let's continue. Our GS2 drive falls into the 115 volt class, and again ours is 10 or 10P2 is, excuse me, not ours is 10P5, so ours is the one right in the middle up there. But we could also, depending on what we needed, we could order one that would have 230 volts going to it, 460 volts going to it, or 575 volts going to it as well. You can see that the different ones, you could have single phase for both the 150 and the 230, or the 230 could also have three-phase input or 200 volt input, but obviously the 460 and 575, those are three-phase inputs. So you can buy different drives for different applications. Again, this is a close-up of that. Specifications for the drive. Ours is the one in the middle, 10P5. Again, it's a half horse, 0.4 kilowatts, and 2.5 is our output amperage. Remember, our motor is calling for 1.65, so we have enough current to run that motor without any problems. Again, there's a lot of information here. I'm not going to go through this because, again, I'm trying to keep this video kind of short for you. This one I put in here because I wanted you to be aware of that first warning that says do not connect external voltage sources to the digital inputs. Excuse me, permanent damage may result. Okay, that is important, so we will talk a little bit more about that later. Below that note, this is a kind of wire that you want to use when you're wiring to those digital inputs. So it should be twisted shielded, twisted pair, or shielded lead wires for the control signal wiring. And the purpose of this is to try to eliminate as much noise on those wires as we can. When you do have a shield on your wires, you need to connect that to a drain or a ground. So we would connect that shield at the drive where we've got our ground indicated on the drive itself, you will notice that it says do not connect the shield on both ends. If I connect a shield on both ends, it becomes an antenna. It just picks up noise. If I connect it on one end to the ground, it's going to work like a drain. Any noise that comes in, that becomes close to that wiring will actually be drained off or go to ground and be removed from creating any noise in your circuit. Okay, this is where you do your programming. So you would actually have to use these buttons here. H in this case that you see lit up is telling me what my frequency is. In other words, this motor is not turning because it has zero frequency. Here is from the user's manual what those different lights and buttons are for. You can see I've got a programming one, I've got a display one, I've got forward and reverse, I've got run, I've got stop, reset, I've got some up and down arrow keys, and I have an enter key. You could run this drive right from the keypad. In other words, we wouldn't need to wire anything to the drive. We could set it up to be run right off that run key and the stop key to stop it. The potentiometer in the middle of that knob can be where you set your frequency. You can turn the speed up or down with that. And of course, your forward and reversing key, of course, you can change the direction. And I'm not going to read through all these. You can definitely take your time with the manual and go through these a little bit closer if you wish. Again, the information on the lights that are on there, and of course there's the function keys. This is where you would go to see what is being displayed on the drive. Remember ours said H0-.0. That was actually showing us the frequency. So if we wanted to display the frequency, we would put in our parameters 0, 0 for that, and that will give us our frequency. If we want to know how fast our motor was going, we could put in 0, 1. Okay. The only other one that we were interested in is how many amps was the motor drawing, so we would go to 0.3 to check our amperage draw. The rest of these would be application requirements. In other words, it might be something that you want to look at based on your application. But those would be the main ones that I would usually set up for my drive. Right here it is showing how to go in and set or program your drive if you wanted to go in and program it from the keypad. So the first thing we're going to do is select a parameter group. So you can see that there are 9 of them. So P0, P1, P2, 3, 4, 5, 6, 7, 8, 9. So there are different parameters that I can go to. And so I go and I push the program button. Remember, there's a button that said program. And then I can use the up and down arrow keys. Once I've chosen the parameter, you just, again, push the program button or the up and down keys to get to where you want to go with which one of those parameters you want to go to. And then once I do, like here I'm showing P0.00. Well, now once I'm in there and I've selected it, I can arrow down until I find the one that I want. In this case, they're using P0.03. So they want to check that parameter. So once they get there, they push enter button. And that's going to take us over to select parameter values. And for the parameter values that I have available to me, I've got 50, 60, and all the way up to 400 if I want to set them. Okay, so at this case, I pick which one of those I want. I push enter. So let's say I get to 60 and I decide that's what I want. I'm going to push enter. And then it's going to end that one, and it's going to jump down to P0.04 to continue from there. There are a couple of kind of basic applications as to what you might want to set up for your drive. That's what they're showing you here for parameters, and it's called the GS2 drive quick start. So here, example 1, this would be setting up for a constant torque application, like for conveyors, compressors, and so on. So what do I need to set up for it? Okay, so the AC drive must, well, in this case, for their application, it says it has to control a 460 volt three-phase motor, and it's a 1 horse. It's an inverter duty motor because they do come up with different motors. You can run a standard motor from a frequency drive. It will not damage the motor if everything is set properly, but it will or will not, how do I put it? The life of the motor isn't as long as a inverter duty motor. Inverter duty motors have heavier windings and better insulation, but a standard motor would work off this as well. Okay, so here they're talking about, okay, what is your horsepower? What is your voltage that you need to put out? So they're choosing a drive for that application. And you can see in that gradient area what it says on the motor, and that's how you choose your drive to match that motor. So you need maximum speed for the motor is 2,000 RPMs. The motor should accelerate. So they've set in 5 seconds, it should decelerate in 5 seconds. So you can set the acceleration times. And let's see, you can set the torque. That's where they set it for constant torque. Their operation of the motor, start, stop, etc. will be controlled by remote control terminals. So that means that I will be wired to an operator's panel somewhere. It says that I'm going to have a remote potentiometer. And so I'm going to use an input voltage, analog input from 0 to 10 volts to control this particular motor application. And they want the motor, the drive itself to display RPMs of the motor. So they want to see the speed. So now they're going to go through what are the parameters that I need to set. Okay, so I've got 460 volts, so parameter 0.00 is where I set my motor nameplate voltage. Then I've got P0.01 is my amperage for this particular motor. My base frequency is set at 60 Hertz. My motor base RPM is P0.03 is 1725. And my maximum RPM is under parameter P0.04 is 2000 RPM. Okay, notice in the warning down there at the bottom, it does say you should never exceed the maximum RPM rating for the motor you are using. And it says if this information is not readily available, consult your motor manufacturer. This your best choice for this, if they do not list it, you're not sure, and you need to get this up and running, set it for the base RPM. You can always go back and change it later if you need to change it. In the red over there, what I'm showing is what I'm setting up, or we're going to set up for our particular drive. So my motor nameplate voltage is 230. My motor nameplate amps is 1.6. My base frequency is 60 Hertz. My RPM was 1660 for this one. And then maximum RPM, according to the nameplate, was 1700. So that's where I came up with those values in red. Okay, stopping method, acceleration time, deceleration time, and frequency settings. So I wanted parameter 1 to be set at 0, 0, and I've got it circled, so that means it's going to ramp to stop. I set my accel and my decel times for 5 seconds. You can see that both of those are listed there. If I do not, if this is right out of the box and I haven't set anything on this drive before, you'll see that the defaults are 10 seconds for acceleration and 30 seconds for deceleration. So again, depending on your application, you may want to go in there and change those. And then of course parameter 2, we want this to be general purpose. Again, we were talking conveyor belts and so on. So I've got that setting at 0, 0. Here's source of operation. Operation determined by external, I've got it circled there. External control terminal keypad. Stop is enabled. So P3 I set for 0, 1. If you go down from there, in this application, that's what I set it for. P4, source of frequency command, I've got it set for determined by the keypad potentiometer. Oop, a little too fast there. Thermal overloads, variable torque, so I've set that one for 0, 1. Again, I've got the user-defined display function. I'd like to see frequency, or I'd like to see frequency. So P8 I set for 0, 0, and that is also the default setting, so that worked out just fine. Okay, if I was going to set it up for this application, and again, this is for setting up the inputs, or wiring the inputs. If I set P3.01 to 2, that would actually be used for my digital inputs 1, 2, and 3. You can see that D1 is my run command. So it runs when it is closed. Okay, it does not have to be maintained. Once I push it, it latches and tells it to run. Okay, D2, or DI2, excuse me, is my forward and reverse. So if it's open, in other words, I haven't pushed the button, it's going to run in forward. Once I push the button, it will change direction and run in reverse. And DI3 is my stop command, so that is a latching input as well. So if I push that down, it will stop. So when DI3 gets no power from DCM, it will shut down. This also keeps DI1 from, if somebody is holding the run button down, it would also keep DI1 from being energized as well. So make that unlatch when I latch in DI3. Okay, on the left-hand side here is a basic wiring diagram. On the right-hand side, it shows you where the wires will be connected up for the different digital inputs, relay outputs, and analog input and analog outputs. So what are we doing here? You can see that forward stop, reverse stop, external fault, multiple speed 1, 2, 3. All of those are shown as DI1, DI2, DI3, DI4, DI5, and DI6 listed on the left-hand side right in the middle of our wiring diagram. All of those get their power from DCM, or complete their circuit through DCM. That dotted line you see wrapped around that, those leads going to the digital inputs, that's actually showing us, or replicating the shield on the wire. So they're even in this drawing telling you should have a shield on that wiring. And in this case, they're grounding it to DCM. Okay, so that's why they tell you not to use an outside voltage source, because if you did, you could actually damage the input going to, or the input card going to this drive. Just below that, you see plus 10 volts, 10 milliamps max, AI, and ACM. What they're talking about there is analog input. So you could, if you didn't want to use the pot to control the frequency by turning it up and turning it down, control the speed, we could actually have some type of analog input to this to control it. In other words, I could remove the pot there and bring in analog input to this to tell it to speed up and slow down. At the very top of this, you see L1, L2, L3. You see some breakers and some inductors there. That would be your line voltage coming into this. So that is showing a three-phase. If we were just using single phase, we wouldn't have anything on L3. Across from that is our AC motor, where you see the T1, T2, and T3. That's where we connect that. Below that is your B1 and B2. Again, that's where we connect up braking resistors if we're using braking on this drive. Below that you see R1, R1C, and R1O. That is a relay output, and it is a single pole double throw switch. So R1 to R1C is actually the common to the normally closed contact, and R1 to R1O would be the common to the normally open contact. When I say common, I'm talking about R1 being common to both the C and the O on this. Okay. Because that is a relay output, it can handle a certain amount of voltage at a certain current level. So if you look at 120 volts AC or 24 volts DC, it can handle up to 5 amps of current. If, however, we're using 230 volts AC, it can only handle 2.5 amps of current. We got R1 and we have R2 below that, does the same thing. And those are programmable. We'll look at that in a minute. Below that is an analog output. Here they're showing it connected to a meter. So if we wanted to see what our analog output was, we could actually, excuse me, I got a little frog in my throat. We could actually see what we are putting out for 0 to 10 volts or 2 milliamps max on that. So we could actually see what our output voltage was on there if we wanted to. At the bottom there, you see that we've got an RJ12 communications jack if we wanted to go that route. The picture on the right is our control terminal wiring. You can see that the first block or terminal block that is shown there is our relay outputs. So we've got the first group is R1, the second group is R2. You get to the next terminal block and you can see that I start with DI1, DI2, DI3, and so on. So those are all my digital inputs, and DCM is my digital common. Next one is analog input, my plus 10 volts, and analog output. And of course my analog common is shown there as well. Parameters. You're going to look at this and I think it's going to be a little confusing for you, so we're not going to worry about this right now, and I'm starting to lose my voice, so I'm going to skip this a little bit. I'm just going to jump ahead. Okay, and again, this one and this one are showing you different parameters that you can set for your drive. Okay, so we start with, in this case, P3 group, the P4 group, and the P5 group. P5 group, multiple speed settings. We're not going to do anything with that for this lab, so we will do something with the next lab with it, so we'll look at it next week for that. There were switches on the top of the drive, and those switches that you see here can set up what you want that analog to be as far as your frequency command. So if I want it to be 0 to 10 volts, 4 to 20 milliamps, 0 to 20 milliamps, I can set those here along with the parameter settings. This is what you're going to look at today, or you should be looking at today. So if I want this setting, so in P3.01 setting 02, this is what I would get if I set it up for that particular one. You can see that, again, DI1 is my run command, DI2 is my forward reversing command, and DI3 would be my stop command. Again, this I'm going to cover next week, so I'm not going to do anything with this right now. Again, the one we're looking at is P3.01 setting 02, so we're looking at the one on the right for this. And you can see that if I've set parameter 3.01 setting 2, I don't have to worry about these other settings on here. So parameter 3.02, 0.03, 0.04, and 0.05, we're not going to do anything with those right now. Like I said, next week we will. Here is our setting for parameter 3.01, so it's a multiple functional. Input terminals DI1 through DI2, and in this case, even DI3 plays a part for this. Okay. We can set up in our parameter 2 settings, we can set up our minimum output frequency, our minimum output voltage, our pulse width modulation carrier frequency. Again, we will look into more of that next week. I'm not worried about it right now. Base frequency, motor base RPM, motor maximum RPM. Again, not worried right now about that. Okay. One you're looking at is that quick start one. So go back to that if you want to look at these. So a lot of these we're going to kind of leave alone at this point just so you can get that first one figured out. Okay. And of course there's our drive. And it says that our input current should be 9 amps. Our output current should be 2.5. Our wire gauge should be 12 to 14. So it gives us some information there. Here's where our connections are located. And again, because we are using single phase, you'll see that one on the right there at the bottom, it says single phase input power. So we use L1 and L2, or hot, neutral, and we hook up our ground. Our output power connections, I got the other red square, and you can see that we're using T1, T2, and T3. B1 and B2 are optional. That's for the braking resistors, and we will not be using that, so we don't have to worry about it. And I think this one you might want to look at, because this is what I want set up for this very first one. So that's how you would wire it into the drive. Notice that I had to cross DI3 and DI2 according to their drawing. You can change that if you wish. You can play around with that, set it up differently if you want to. But that's what our wiring would look like going to our drive. Okay, again, I want to stop this video because I'm probably boring you to death.